So I guess we can start. Today we have with us Eleni Rosalina Andrinopoulou. So Eleni has a bachelor from our Department of Statistics, and she has obtained a doctorate from Erasmus MC Department of Biostatistics and Department of Cardiothoracic Surgery. She has experience as a researcher at Rotterdam Eye Hospital and a postdoctoral fellow at Erasmus MC Department of Biostatistics and Department of Epidemiology. And now she works as an assistant professor of biostatistics at the same university department. So it's a pleasure that Eleni is with us today, and she's going to speak about investigating the impact on dynamic predictions and effect sizes when misspecifying the association between outcomes. So Eleni, please, you may start your presentation.
Thank you very much. Thank you also very much for the invitation and giving me this opportunity to present here today my work. So I will start with the motivation of my research. So nowadays, we are flooded with a lot of information in our daily life, and the same also happens in medical healthcare. So for example, because we have electronic medical records now, it is very easy to follow the patients from the moment that they're born until the moment they're dying. And therefore, you can imagine that a lot of big data is available in many medical fields. And the different types of information that could have is like such baseline covariates. So for example, we could have the gender of the patient, so it doesn't change, remains the same, or we can have some genetic information like the blood type. So this information that doesn't change that we have. We can also have information that changes over time. So these longitudinal outcomes, how we call them. So for example, every year you will go to your doctor and you will perform some blood test. And this will be repeated every year in order to see if everything is fine for you. And of course, we have events that can occur during our life. So for example, some patients could experience some cancer, or they could die, they could start a treatment. So there are many events that could influence all the longitudinal outcomes, but also our health. And you can imagine that big data, it's very good, it's the key tool to new developments in our research. But of course, it can be very challenging when you're trying to combine all these different things, and especially when we have different types of information. So some applications that I have been working on. So I have some collaborations with some departments inside and outside Erasmus Medical Center. And these are with the rehabilitation department, where we have some stroke data, with the head and neck cancer, where we have some quality of life data, and the cystic fibrosis foundation. So for the stroke data, it is very important for the clinicians, but also for the patient, to be able to predict what the outcome will be after 6 months of having the stroke. So in particular, when someone has a severe case of stroke, he can have some problem with his functionality. So for example, he might have difficulties in moving their hands, their legs, have some difficulty in the speech, they won't be able to talk or to dress up themselves, to go to the bathroom themselves. So it is important for the physician to follow those patients over time. And they do that by collecting a number of scores. So you can see them here. We have the Action Research Arm Test, the Fugl-Meyer Upper Extremity, and the Partel Index. So these are some important scores that physicians are collecting after the stroke. And depending on the score that they get, the values that they get on these tests, then the physician could decide what's the appropriate treatment strategy for this patient. And it is also expected that after 6 months, the patient cannot change anymore. So it is very important to be able to give the appropriate treatment in this period. Another example, from the head and neck cancer. So it is clear that after a patient has cancer, his quality of life could be changed. And therefore, it's very important to follow those patients to see how they're deal with this disease in their life, and if it's improved, if they can improve it, if they are getting used to that. So it's very important to follow that. But of course, they are also in a high risk of experience a recurrence. So cancer, unfortunately, can come back. And therefore, it is important to be able to predict that in order to take the measures needed. And finally, for the cystic fibrosis, this is a genetic disorder. So patients are born with that. It's in their genes. And this is a disease that influences all the organs in our body, and it has a huge impact in our lungs. And therefore, it's very important to measure the FEV1. So this is a score that tells us how much oxygen the patient can inhale. So of course, if the lungs are working really hard to keep up with the oxygen level, then there is a chance that the body is working too much. And even if the patient is eating correctly, is eating a lot, the BMI could drop. And therefore, normally the FEV1 score is measured together with the BMI of the patient in order to see how the organs and how the disease is evolving. And of course, these patients are of high risk of death. So 20 years ago, those patients wouldn't even reach their 50s. They would die before they reach the 50 year of their life. And therefore, as you can imagine, it's very important to be able to follow them in order to extend their life. And because we are able to follow them and to measure all these oxygen level, new medication has been developed, and now patients can reach up to 80 years of their lives. And another risk that we have is exacerbation. So patients are of high risk experience exacerbation, which are the events where the patient needs to be hospitalized. So they have to go to the hospital in order to receive intravenous treatment. And this could happen multiple times during their life. So these are very, very important outcomes that we need to follow in order to be able to provide them with the appropriate treatment. So normally in common practice, when we are reading a medical paper, we'll see that all these outcomes within each field, they're analyzed separately. So you would see one paper presenting, for example, an outcome for the arm when we are talking about stroke patients, and then another article talking about the leg. And also, if we have survival outcomes, you would see that all these survival outcomes are analyzed separately from the longitudinal outcome. And I will show you some examples here. So from the stroke data, we analyzed 412 patients that had a severe stroke. And during their hospitalization, but also later when they went to the rehabilitation center, we measured the Fugl-Meyer score. So in this figure here, you can see in the x-axis the time until stroke. In the y-axis, you can see the Fugl-Meyer measures. Low measures mean that the patient can't really do anything, so his functionality is not good. And a high value, so I think the maximum is around 67, means that they can function normally like everybody else. So they can move their hands, they can open a door, they can grab something, they can undress themselves, and all these simple tasks. So the circles in the plot represent the observed value that we get. So every time that the patient comes into the clinic or into the rehabilitation center, we get one of these extra points. And then the solid line and the shadow represents the prediction, the mean prediction, and the prediction interval. And you can see that every time that the patient comes, we can update those prediction in order to be able to adjust their treatment or their physiotherapy. And of course, the main goal in this project was to predict whether a patient will be a recoverer or a non-recoverer, because it's the case that when you have a stroke, you are not able to move anything, but of course, after a few weeks, you start moving your hands a little bit, your legs, and it really depends on the severity of the stroke that you have, what you will be able to do at 6 months, which is the last point that they normally have physicians. And therefore, we predicted also in which cluster they will be. Cluster 1 means that they are no recoverers, while cluster 2 means that they recovered. So this is also easy to interpret that either to the physician and to the patient, of course. Another outcome that we have is the action research arm test, or the so-called ARAT. Here we had 450 patients. Again, in the x-axis, we can see the days after stroke. In the y-axis, we see the ARAT measurements. So the lower the ARAT, it means that the less they can do, less the functionality of the patient, and the higher it means that the more they can do, they're more functional. Again, the circles represent the observed value, and the solid line with the shadow, the prediction and the predicted interval. I would like also to inform you that these models, so this one and the previous one, are already implemented in the clinic. So now when a patient comes with stroke, the physician can open the website that we have and then get the prediction for his particular patient. There have been discussion whether we should show these plots to the patient, because involving the patient is very important nowadays in order to make a common decision making. However, we are still scared that if we show those prediction plots to the patient, they might get disappointed, and then this will influence their recovery. Another application in the head and neck cancer. So here we had 293 patients, and we investigated the quality of life measure. So we have lots of measurements in quality of life. Here we only focus on the voice handicap index, as you can see here. And in these plots, we have two different treatments. So we have the more conservative treatment and the surgery treatment. Again, you can see as more measurements we have, the predictions are updated. And in that case, a doctor can decide, okay, which treatment is best for the patient. So up to now, I showed you how to analyze those outcomes separately. But of course, it might be of high interest to analyze them together. So here there is an example that I'm working currently with my collaborators in the head and neck cancer. So what we want to do is to predict the recurrence of cancer, so the probability that the cancer will come back, if we use the quality of life measure. And of course, because the quality of life measure changes over time, it is good to update also the probabilities. So let me explain you a little bit what we see in these plots. Again, we have the two plots for the two treatments. X-axis here, we have the time since they were diagnosed with cancer. In the y-axis here on the left, we have our longitudinal outcome quality of life. And on the right side, we have the event-free probabilities. So you can see as extra information is available for the quality of life, the prediction for the event-free probability is updated. So for example, you can see for the conservative treatment here that the probability is really high in the beginning, while for the surgery is low, but as more information is available, those probabilities become similar. So this is very important for the patient in order to decide whether they want the difficult surgery, let's say the painful treatment, or a more conservative that doesn't hurt that much. Another example of combined analysis is with the cystic fibrosis data. So we used patients from the US registry data. We have about 17,000 patients. And what we want to do is to investigate whether, including in our model, the FEV1 measurements together with the BMI could help us predict when the patient is going to experience exacerbation. So here we have in the x-axis the age of the patient. The y-axis, we have the two longitudinal outcomes, so the FEV1 and the BMI. And on the right side, we can see the event-free probability of exacerbation. Those plots are the same, just duplicated. So you can see how the risk changes as more information becomes available for this patient. So it is clear that a lot of information and a lot of outcomes and a lot of different types of information is available in each of these fields. But when I check the literature, normally they will analyze everything separately. So they will analyze, as I mentioned before, separately the arm, then separately the leg, or separately the longitudinal outcomes, separately the survival outcomes. But intuitively, when a doctor sees a patient, they will investigate everything, all the outcomes that they have on them. So it's not that when we have a patient with a stroke, one doctor will check his arms, one doctor will check his speech and the other doctor will check his legs, but one doctor will check everything together, and depending on those scores, he will decide what kind of treatment or physiotherapy this patient needed. But when we look at the statistical analysis and the clinical papers, then normally they're using all these outcomes separately. So I'm wondering whether statistically we can also combine everything in one model. Now I will introduce the statistical models. So first of all, in a very simple case, when we have one longitudinal outcome. So if we have one longitudinal outcome, a popular framework that we could use is the mixed effects model. So this is presented here, and it consists of the fixed effects and the random effects. So the fixed effects denote the average evolution of all patients over time, whereas the random effects denote the subject-specific evolution. And this is also the part that accounts for the fact that we have multiple measurements within the same patients. Because, of course, you would expect that measurements from the same patients will be more correlated than measurements from different patients. And of course, we assume the simple distribution, the normal distribution for the random effects and for the error terms. So what if we have now two longitudinal outcomes? So as I showed you in all the applications, we never had one longitudinal outcome because normally we measure lots of things. Physicians like to measure lots of things. So in that case, what we could do, we could extend the multivariate mixed model. So what we could do here is to assume one mixed model, linear mixed model for one outcome, another one for the second outcome, and then we can assume that they are correlated through some random effects here that follow the normal distribution, and they have a common variance-covariance matrix. So this is a way to assume that those outcomes are correlated, but the problem here is how do you quantify this association? So this is actually a problem that I had with my collaboration, that if I would fit this multivariate mixed model, linear mixed model, then the next question would be, okay, but how is this correlation strong? Is it weak? How do I specify that? And as you can imagine, if the correlation is only through the random effects, it's very difficult to interpret that. So how do you interpret a high correlation between the random intercepts, let's say, of the two models? It's very difficult for the physicians to understand that. That's why, what I thought of is to include a functional form of one longitudinal outcome into the main, let's say, clinic longitudinal outcome. So we can have, for example, a function of the second longitudinal outcome into the first longitudinal outcome, and then in order to interpret their correlation, we have this association parameter here, alpha, which can be interpreted as a coefficient, as any other coefficient that, even physicians are familiar with from simple regression models. So a way, let's say, to include one outcome into the other is to use the underlying value as the functional form. So in that case, I include the fixed effects and the random effects of my second longitudinal outcome into my first longitudinal outcome. And of course, it's difficult. Again, it's still difficult to explain to the physicians what underlying value is. And the other challenge that we have here is that this is not the only option that we have. We are talking about repeated measurements, so we could have other functional forms that could describe the association between those outcomes. And this is normally what I'm presenting in the plot in order to explain how these associations work. So we have two figures here for the two longitudinal outcomes. So let's assume that we have y1, y2, two continuous longitudinal outcomes. The circles represent the observed value that we have, the solid line, the underlying value, and then the dashed line represent, for example, two time points where we want to assume an association between those outcomes. So if you can see in the second plot here, the underlying value at time 1.5 and at 8 seems to be very close. But if you look at the slopes, which are denoted here with these purple short lines, you can see that they're opposite. So in that case, we have a decreasing slope, whereas here we have an increasing slope. So this shows us that just assuming the underlying value might not be appropriate. So yeah, one option is to have the underlying value as shown here. So two longitudinal outcomes are connected together at the same time point. Another option is to have the slope. So at each time point, we assume the connection to be happening via the slope. And we can include that, we can translate that into our statistical model by including the derivative of the second longitudinal outcome. Another option is to include the whole area under the curve. So instead of ignoring all the previous measurements, we can take them into account. And this could be translated with the integral. So we assume the integral of the underlying value of the second longitudinal outcome to be included in the first longitudinal outcome. So in some of the applications that I showed in the beginning, we had also survival outcomes. So it is of interest to analyze longitudinal outcomes and survival outcomes together. So in that case, we can extend our mixed model, our linear mixed effects model, to handle also survival outcome and use the so-called joint models of longitudinal and survival data. So again, here we have, let's say, two longitudinal outcomes, and then we have a relative risk model in order to account for the survival outcome. And again, as we did before, we can include the functional form of the longitudinal outcome 1 and of the longitudinal outcome 2 into the survival model. And these parameters alpha, S1, and S2 will denote the association, and they are interpreted as hazard ratios, where physicians are very familiar with. What happens now if we also want to assume associations between the longitudinal outcomes, but also associations with the survival outcome? Of course, I can extend my model and make it as complicated as I want. So for example, here I can decide that my second longitudinal outcome is included in the first longitudinal outcome, but only the first longitudinal outcome is included in my survival model. And as you can imagine, I can have different options. However, I will stop here. Otherwise, I will not finish the presentation today, I think. So you can easily extend those models by assuming any different association that you would like. And a problem that comes here is that if you have lots of longitudinal outcomes and lots of functional forms, how do you know which ones to choose? If you ask the physician, probably it's difficult to tell you. From my experience, when we are dealing with such complicated association structures, it's difficult to give you an idea of what they are expecting. And therefore, what we have proposed previously is to assume shrinkage approaches in order to decide which outcomes, but also which functional forms are more appropriate. So the main goal of these models is to provide personalized dynamic predictions. So the physicians, first of all, of course, they want to investigate whether there are associations, but the ultimate goal is using those associations to obtain predictions for the patients. And of course, since we have longitudinal outcomes, those predictions could be updated, and this is what we call dynamic predictions. And of course, you don't want to predict the average patient, because this is very, very difficult. So you have severe patients, but also more mild cases. You don't want to put them in the same basket. So what you want to do is personalized prediction. So using the models that I presented before, we can assume a new patient L, and then using all the information that we have, so all the baseline information that we have on the patient, but also the longitudinal outcomes that are updated each time that they come to the clinic, we can obtain future measurements of these longitudinal outcomes, but future risk of event. And of course, we have to set a medically relevant interval in order to obtain those predictions. So for example, in the stroke case, they were really interested in 6 months after stroke. So we define this interval here as T until T plus delta T. And of course, based on the models, we can calculate these measures here. So in the first case, we have the probability of having an event within this interval, so up to the time t plus delta t. So this is the probability actually of surviving until t plus delta t, given that no event occurred up to then, and all the information that we have of the patient. So all the longitudinal measurements, but also some other baseline information that we have for the patient. And the same holds for the longitudinal outcomes. We can calculate the mean value of those future measurements, given, of course, that the patient didn't experience the event, and all the previous information that we have, plus the baseline covariates. Okay, so now we can calculate these measures. The next step would be to investigate if these predictions actually are good. So before giving the model to the physicians and put it into the clinic, it's very good to know if those predictions are valid. And therefore, we can investigate the predictive performance measurements of those predictions. And for the longitudinal and the survival outcomes, so basically for all outcomes, a simple way to do that is to investigate the distance between the prediction that we got and the actual observed value that we have. And in the survival, we have an extra measure, the discrimination ability. So how well can the longitudinal outcome discriminate between patients that have high risk and patients that have low risks? And yeah, in this paper, we have investigated all these measures in different settings. So now, yeah, I will investigate what happens if I misspecify the association between the outcomes. So what happens actually if I don't know this association, I assume a specific association, but this association is not the correct one, because this is also what happened in practice. It's very difficult to know the true association between your outcomes. So most of the times we will have misspecification there. And therefore, I was really interested to see what's the effect actually in the effect size, but also in the predictive performance, because this is what we are using at the end. First of all, I will investigate the fitting. So what's the impact in the effect sizes when we have a joint model. And I will do that with simulation, because this is the only case where we know we know the gold standard. In my applications, I have no idea what the gold standard is, what my associations are, but in my simulation settings, I can assume that. So here I simulate two outcomes, one longitudinal and one survival. For the longitudinal, I assume a nonlinear time or nonlinear time evolution trajectory, and I assume also a treatment effect. For the survival, I assume the treatment effect, and then I include the underlying value of the longitudinal outcome to my survival outcome. And when I fit, I keep most of the things the same, except the association between the longitudinal and the survival, where I misspecify that and I fit a model with the slope and the area. So here we can see the results. Each of these panels represent a different coefficient. The first row represents the coefficients for the longitudinal model, while the second row represents the coefficients for the survival outcome and model. Within each panel, we have two box plots, one for each model. In the first case, we have the area association. In the second case, the slope. The vertical lines here represent the true value, so what I simulated for. So what I observe here is that when I see, when I check the area model, that most of the parameters seems to be correct, really close to my true parameter. However, when I assume the slope parameterization to fit my data, then I see that the values are really biased. They're underestimated here, and even for the association, it's really far away from the true association. So this is very concerning, and it makes me believe that you really need to have to fit the correct model in order to get not biased results and to give the correct association parameters to the clinicians. So another question that I had here is, okay, if I don't know the association parameter, what happens if I include all of them in one model? Will my model be able to distinguish between the true effects and the no true effects? So in that case, I assume a model where I include all the parameters. So the last line here represents the different parameters that I have for my model. And as you can see, I include all of them. But remember that I simulated only from the value. And as you can see, yeah, I have 1.2 here, 1.1 thing, and it's really close to the real one. And then my model here predicts 0 for the slope, which is true because I didn't simulate from the slope parameterization, and the same happens for the area parameterization. And I did the same when assuming shrinkage parameter. So I was very happy to see that the results are the same, but it was also expected because in that case, we're applying shrinkage in only 3 parameters. I would expect that the results would be a little bit different, and probably the shrinkage model will work better if we had more longitudinal outcomes and even more parameterization. So in that case, again, the parameter seems to be fine, just they're shrunk more towards 0, which is expected. So now I will continue with some simulations when assuming multivariate longitudinal outcomes in the case of the joint model. So here I simulate 2 longitudinal outcomes. So one is more complicated. I have a nonlinear time, a treatment parameter, and then I include the underlying value of my second longitudinal outcome into my first. Then I have a more simplified model for the second longitudinal outcome, where I include only a linear time here, and I have a survival outcome where I include treatment, and I include the underlying value of my first longitudinal outcome. And when I fit the model, I ignore the association between the 2 longitudinal outcomes. So in that case, I have to admit that there were some models that didn't converge. So for me, this tells me that if you are misspecifying a model, then probably you will get some convergence problems. And in that case, yeah, the parameters, the true parameters, are really not close to the obtained one. So you can see they're quite far. Most of them are really off. So I cannot trust the results in this case. Now I will move to the predictions. Okay, until now I investigated the impact when we had misspecified associations of the association parameters. So I investigated the impact of the coefficient, but what happens to the prediction? So how does that influence my predictive performance? So first of all, in the joint model, so what I did here, I simulated data set, then I split them in 5 subsets. I used 4 of them to fit the model, and then I left one subset out, in order to obtain my predictions. And then for this one subset, I calculated the AUC, so the discrimination error, and the prediction error, which is the distance between the actual value and my prediction. Again, I simulate now a longitudinal outcome with nonlinear time treatment, and then a survival outcome with treatment and the underlying value of my longitudinal outcome. And when I predict, I tried different parameterizations. So I have my value, which will be here my gold standard, the slope, and the area. So here we have 2 plots, one for the AUC, the discrimination, where higher values are the best, and one for the prediction error, where lower values are the best. So the solid black line here represents the value parameterization, the dots, the blue dots, the area, and the dashed purple line, the slope. So you can see here that the area and the value are really close to each other, which I would expect that because the area includes also the underlying value. But the slope parameterization seems to not perform that well. So you can see how the AUC sometimes reaches 0.5. Now, if we look at the prediction error, we see the same pattern. So the value and the area seems to be very close and also lower, but the slope parameterization seems to increase our prediction error. And now I did the same, but instead of simulating from the value, I simulate from the slope. In that case, surprisingly, I didn't see a lot of differences, so I'm not sure why this is happening, but I would like to repeat this simulation when I assume a more complicated model and see if the same comes here. But in that case, you can see that the differences in the AUC and the prediction error are not that big. And finally, I simulate from the area and I fit the other models. Here again, you can see that the value and area are close. And yeah, I mean, sometimes you see that the slope is also close to them, but not always. So again, my conclusion here is that, yeah, that the value is really close to the area, which makes sense because I would expect that the underlying value is included into the underlying, into the area of the curve. And now focused on the longitudinal outcome. So what if I have multivariate mixed model? So in that case, I did the same. I split the simulated data set in 5 subsets. I used 4 of them to fit the model, and then 1 to get the prediction. And then I calculated the prediction error, so the difference between the actual value and the prediction. And another feature that we have here is that predictions are updated dynamically. So I investigated the prediction in each scenario. So when I have one observation and the rest I predict, when I have 2 and I predict the rest. So all these scenarios were investigated because I would expect that the more information we have, the best the prediction becomes. In that case, I simulate 2 longitudinal outcomes. Longitudinal outcome 1 has a linear time treatment effect, and then I included the value and the slope of the second longitudinal outcome. And the second longitudinal outcome is a simple model that includes only linear time. And then when I predict, I assumed that I have only the value. So basically here I assume 2 sets of data set, 1 for the value, 1 for the slope, and then I'm predicting using the value. In that case, yeah, I have the results for both outcomes, so outcome 1 and outcome 2. The first panel here is the gold standard, where I simulate from the value and I predict the value. And the second is the scenario where I simulate from slope and I predict the value. So as you can see, if we focus in this panel here, the more information I have, the less the error becomes, which is something that we expected. And then if I compare it to the misspecified model, you can see that, okay, when you have one measurement and you predict the rest, then the errors look similar. But if you have more information, it seems that the error does not become better when I have my misspecified model. And yeah, this is these are the results for outcome 2. I don't expect big differences because if you remember, I include outcome 2 into my outcome 1. So my outcome 2 didn't have a lot of influence in this misspecification. Then I simulate from the value and area of the second outcome, and then I predict the area to see what's happening there. Again, this plot will be my gold standard because I simulate from value and I predict the value. And in this plot, I simulate the area and I predict the value. We can see something. We can see the similar things here. So first of all, that the more information you have, the better the prediction becomes. But when you misspecify that, you see that the prediction error is not getting any better. And of course, they're much higher than in the gold standard case. Again, for outcome 2, since I didn't include any association in that model, I don't have a lot of differences between the correct model, the gold standard, and my misspecified model. So I have a lot of results. I performed a multiple simulation scenario, but of course I can't present everything here. So my general conclusion would be that we have a lot of information, and intuitively physicians will use this information. So it's not that one doctor will check your arm, the other doctor will check your leg, the other doctor will check, I don't know, your brain. Is normally you have one doctor that will check everything, and then they will propose the best treatment or treatment strategy for you. But when it comes to the statistical analysis and to scientific journals, all these outcomes are analyzed separately. So it makes sense if we try to fill in this gap between the clinical practice and the statistical models and try to do the same. So model everything together in a nice model and try to predict something using all the information that we have available. Of course, we have lots of challenges, as we saw. So for example, which outcomes to use, which outcomes to include in which model, and how do we correlate these outcomes. So in the case, for example, that we have multiple measurements per patient, so these longitudinal settings, we can have different ways of modeling the form of association. So as we discussed, we can have the underlying value, we can have the slope, and of course both of them are really important, so we need to investigate which ones should provide us with better predictions. And of course, yeah, we saw that from the simulation, at least for me, it was clear that if we have misspecifications in our model, then we are more likely to get biases in our effect sizes, but also in our prediction. And this could influence the patient's outcome. So we could incorrectly give the wrong treatment to a patient because, yeah, we misspecified the model. So we have to be very careful on how we use the models and how we specified all these associations. So thank you very much. I'm happy to answer any questions or receive any feedback that you have. Thanks.
Thank you very much, Rosie. So are there any questions? So can I ask one question, Rosie? So if I understood correctly, what you do is actually to, let's say you have two outcomes, and you kind of combine the results from the first mixed model to the second one. You plug in some estimates.
So yeah, it's if I understand it correctly, you're mentioning, yeah, you're referring to a two-stage approach, but I'm not doing a two-stage approach here. I'm having a single model that all the parameters are estimated simultaneously, so at the same time. Of course, yeah, we could do some simple two-stage approaches where you first, for example, fit longitudinal 1, then you fit longitudinal 2, and then you include, for example, the predicted values or the coefficient or whatever into one. But in this case, everything happens simultaneously at the same time. So the model is specified as one.
Okay, so does it, my question was actually referring to the fact that, does it actually, the result depends on which outcome you are going to consider to plug into the second. For example, you take the second one and you put it as an explanatory variable to the first one. Does this order makes?
Yeah, that's a really good question. So this is also something that I am struggling with, because of course, if I associate them without this structure, then they're associated only via the random effects. And then of course you have the problem that you can't interpret that to the clinicians. They have no idea if the association is strong. But then of course, if you want to include one into the other, we need to make the decision which outcome is our primary outcome. Okay. And this is something, yeah, that struggling with, and I don't know what the input change those. So does it really matter? I guess ideally I would like, for example, if I'm predicting arm, then to include the leg. But then if I'm predicting leg, then I would like to include the arm measurements, right? But I don't know if I include them both inside, if that would be a problem. So I'm yeah, because these models are already complicated, and I'm scared that if we complicate it even further, then the whole program will crash. But this is something, I guess, yes, decisions that we need to make, and in order to get the correct estimates and the predictions. But that's a really good point that I'm also struggling with.
Yeah, I guess it's difficult to evaluate it somehow, but in any case, yeah. And
yeah, I mean, you need also the help of the clinicians, right? You are trying to make a model that clinicians will understand, and that's why you need also their input in order to tell you which outcomes are important and which ones to include. I mean, in a simple regression model, you have the same problem, right? You need to decide which predictors to include in which outcome. So I guess it's kind of a similar problem.
Yeah, and yeah, that's interesting. And another thing, so it seems consistently in your results that the area parameterization is the best one. So is this reflected to real data? Because I think you showed only simulated results for simulated data.
Yeah, so it's very difficult to investigate that in real data because we don't know. So I have no idea.
In terms of prediction, so you can split a real data set to subsamples and then
you're right. So I could do the same thing with a real data set. I haven't done that with a real data set because I wanted to decide, okay, which scenario I'm going to use, because you can imagine that I could continue with my simulations for I don't know, infinity time, because there's so many things. And I didn't present even everything because it's too many.
Okay,
but I would like to, this is a good thing that when I decide which ones I would like to do, then I could try it in some application. And also it would be interesting to see if in one application it works different than in the other application. But first I want to get a general idea from the simulations.
Yeah, of course. That's what we almost always do. Okay, are there any other questions for Rosie? So I guess we are done. Rosie, thank you very much for your nice talk.
Thank you. Thank you for the invitation.
And hopefully we can meet at some point if you visit us in Athens.
Yeah, I will let you know when I'm in Athens.
So take care and all the best.
Take care.
Thank you very much.
Bye.
Bye-bye.